Today we're going to tackle a problem dealing with radioactive decay, the integrated rate law, and half-life. So the biggest thing with this problem is knowing the process and also watching your calculations and your units. Those are the biggest downfalls. So a moon rock is this old. Currently it contains this amount of uranium. Initially it did not contain any lead. What is the current mass of lead in the rock? And we're given the half-life. So given the fact that this is a problem dealing with concentration at an amount of time, we know we're going to use the integrated rate law for first order, since radioactive decay is first order. In order to use this equation though, we have to have the K value. So with the half-life, we can find the K value. This is our half-life. And I would always recommend just writing in the units and everything kinetics, because sometimes they'll give you like minutes and seconds, and if you don't write it out, what might happen is you might not even catch your mistakes. So this, we get K of around 1.55 times 10 to the negative 10 years. Okay, so we're gonna put K in here. And for concentration, we don't need concentration, because since concentration is equal to this, and mole is equal to mass divided by molar mass, when you put this side under here, essentially you're just going to cancel out, and you can just basically put your mass in here. So what is the mass at a given time that we're told? The current mass is 1.18, so we're going to use that. But 1.18, that is the mass remaining at what time? So the time that we should be using here is actually 3.8 billion years old. But we don't want billion years old, we want it in years, because our K here is in years. We want to make sure our units match. So then you might say, what does all of this have to do with lead? We'll get to that. So 3.8 times 10 to the 9, that is a billion years. Plus ln, the initial concentration. So what we want here, the question is saying you have a rock it starts at its original rate, and then it being 3.8 billion years old, that means after 3.8 billion years old, it only contains 1.18 grams left. So after 3.8 billion years old, it only contains this amount. So then we want to find out, what does this have to do with lead? Lead is part of this reaction, it's part of a decay. When it decays into lead. So this entire circle is the original concentration. The amount of lead that it contains now is the amount that has decayed, so that's everything else. So what that tells us is this large circle, this large rock, has an initial mass, and then you must take away the reacted mass to find the current mass remaining. So our lead here is the amount that has reacted, because the amount that has reacted will turn into our lead. So this is a very important, you can call it an equation, that you will use for every kinetics problem that has to deal with reactions. So what are we looking for here? We're looking for the initial amount. So the other catch to this problem is you want to make sure your calculations are right. Even though you got the steps right, you can still calculate incorrectly. So let's try this. So notice how this is going to be added to the left side. And the original amount of uranium is going to be around 2.13 grams. Let's make it more precise. So very easy to mess up here. This is actually going to be added to the other side, not divided. So then we found the amount initially. Now that we know the initial amount and the remaining amount, we can find the amount that has reacted to yield lead. So the initial amount being what I have boxed here, and then we don't know the reacted amount, but we do know the remaining amount after 3.8 billion years old. That's 1.18 grams. And that tells us 9.47 grams of uranium has reacted to form lead. And since they are a 1-to-1 stoichiometric ratio, we can just say, we don't need to like do any molar conversions. But the thing is this is the amount of, this is a mass of uranium that has reacted. But now we want what is a mass of lead. So we need to do a little thing here. So essentially we know from the question here that the ratio of uranium reacting to lead is going to be 238 grams of uranium will give you 206 grams of lead per mole. And this is the amount of uranium. This is uranium and this is lead. And these are isotopes, so you want to use what they write here for your amount here. So then doing this thing here, if we put out to the calculations, essentially that tells us that's around 0.82 grams of lead is produced. So to recap, we used these two equations and also this very important equation and also this conversion factor. You could also do like mole to molar mass and mass to molar mass, what have you, but this is definitely the fast shortcut to use and to get the right answer.